Okay, so in this video I'm going to be introducing some properties of integrals, and then we'll look at an application of how the integral can be used to calculate average values of a function. So first, let's look at properties. So first property is that the integral from b to a f of x dx is equal to the integral from a to b f of x dx. So in other words, if I do the integration in the opposite order, then I pick up a negative sign. Next property is that the integral from a to b plus the integral from b to a, b to c, is equal to the integral from a to c f of x dx. And so I think this property is fairly easy to understand if we draw a picture. So if I want to find the area underneath this curve, I could just find the area from a to c using this integral over here, or I could find the area from a to b, then the area from b to c, and add those two things together. So sometimes it can be useful, for example, if you have a piecewise function where the definition of the function changes depending on different locations, that you might want to split it up into different pieces like this. Okay, next, if little m is the minimum of f of x on some interval, and capital M is the maximum, then we have some inequalities. Little m times b minus a is less than or equal to the integral, which is less than or equal to capital M times b minus a. So again, I think this property is best illustrated by a picture. If I have some function like this, then little m is here. So what this is saying is that if I make a rectangle with width of b minus a and height of little m, that's an approximation to the total area under this curve, so it's an approximation to the integral, but it's always going to be an underestimate since the height of our rectangle was the smallest value the function could take, so everywhere the function is going to be bigger than that, so the rectangle is always below the graph. Whereas if we use the biggest value of f, capital M, we can approximate the area with this rectangle, but now the rectangle is always above the graph, so we're getting an overestimate. So that's really all these equations are saying. Then the next property is that if we have the integral from a to b of a constant times f of x dx, then it's equal to that constant times the integral from a to b f of x dx. So you can pull a constant outside of the integral. Then lastly, the integral from a to b f of x plus g of x dx is equal to the integral from a to b f of x plus the integral a to b g of x dx. So if you have an integral of a sum of two functions, you can split it up into the sum of the two integrals. So just like what we did for derivatives, basically instead of trying to calculate the derivative of something complicated, you can split it up into derivatives of smaller, simpler pieces, and you can do a similar thing with integrals for sums and differences. I could just as easily have had a minus sign here and it would still be fine. Okay, so let's look at an example where we use some of these things. So first off, let's look at integral -1 to 1, let's say, of x squared plus absolute value of x dx. And actually, just to make this a little bit more interesting, let's change this to +1 to -1. That way we have to use one extra property to figure it out. So this, first of all, if you get something weird like this where the smaller value is on top and the bigger value is on the bottom, then the first step is to use property 1 here to flip the order of integration, but you pick up a minus sign. Then you can also use property 5 that we just discussed to split this up into 2 separate integrals. Okay, so now let's look at this absolute value of x piece. If I want to use fundamental theorem of calculus, I need to have an antiderivative, but that's hard to do for absolute value of x. And so let's take a look at the absolute value function. So this function here is defined piecewise, and so if x is positive, then it's just equal to x. We certainly can find an antiderivative of that. If x is negative, it's just equal to negative x. Again, it's easy to find an antiderivative of that. So if we could split it up into regions where either x is always positive or x is always negative, then we could do this using fundamental theorem of calculus in a relatively straightforward way. So to do that, we'll use property 2 up here and rewrite this as an integral -1 to 0 absolute x dx minus integral 0 to 1 absolute x dx. Then this x squared one we can evaluate right away with the fundamental theorem. Now, if we use the definition of absolute value of x over here, on this region, we get negative x from this lower one. So it'll become integral -1 to 0 x dx. Then we have minus. On this region, it becomes positive x. And then here, what do we get? Let's see, it's 2/3, I suppose. Right, so you plug in 1/3 and you get 1 -1/3. Then you plug in the minus sign, you get a minus, but then also a minus from the evaluation of the definite integral. So those minuses cancel, and you get 2 minus 1/3, so it becomes -2/3 overall. Then we can evaluate these other integrals using the fundamental theorem now. So we'll get 1/2 x squared -1 to 0 minus 1/2 x squared 0 to 1 minus 2/3. And so this one will give us -1/2. This one will give us -1/2. Then we have -2/3. So it looks like overall we get -5 divided by 3. So that was an example where we needed several of these properties that we discussed. So we used property 1 in this first step to change the order of integration. We used property 4 to split it up into a sum like this. We used property 2 in order to rewrite this integral of the absolute value function into an integral with 2 pieces. And we also used property 4 here. Remember there was a minus sign here. That's a constant, like this k, that we factor out of the integral and cancel with the minus sign that was out front. And then once we had all those simplifications, we could use the fundamental theorem to calculate the integral. Okay, so now I'd like to move on to a couple more useful properties to keep in mind. So the first one is if f of x is an even function. So remember, even means that f of x is equal to f of negative x for all x values. So if we have this, then the integral from negative a to a f of x dx is equal to 2 times the integral from 0 to a f of x dx. So the reason for this is just that if you have an even function, then it's symmetric about the y-axis, so the area to the left of 0 is the same as the area to the right of 0. So we just calculate 2 times the area to the right of 0. So sometimes this can be useful. A more useful one is something that you saw in the homework. So if f of x is an odd function, which recall means that f of x equals negative f of negative x, then integral from negative a to a f of x dx is always equal to 0. The reason for this is that these sorts of functions have a symmetry like so, and therefore whatever area we have from 0 to a, the area from 0 to negative a will just be negative that area, so it'll cancel out and we'll get overall 0. So for both these properties, it's important that the interval we're integrating over is symmetric. It's from negative a up to the same value, positive a. So this can be useful sometimes. For example, suppose I want to calculate integral from negative 72 to 72 of sine of x. Well, this would probably be somewhat of a pain to do, especially since I don't want to rewrite the antiderivative of sine would be something with a negative cosine, and I'd have to calculate like cosine of 72. I don't really want to do that. But sine of x, we know, is an odd function, and so therefore without doing any calculations with the fundamental theorem, I can immediately conclude that this is 0. So this is an example of how this factor of odd functions can be extremely useful and save us a lot of work. This thing with even functions is sometimes useful as well, but typically if you can calculate this integral on the left, then you can calculate this integral on the right, so it doesn't save you a massive amount of work. But sometimes it can still be useful to have this. Okay, so the last thing I want to discuss is the average value of a function. So I don't think I'm going to go through the derivation of the result in this video. You can find a sort of heuristic argument in the textbook for why this formula I'm about to give you is true. But the end result that you arrive at is that the average value of f of x on the interval a to b is equal to the integral from a to b f of x dx divided by the length of the interval, so b minus a. So this sort of makes sense. If you think of an average value as a sum of a bunch of values divided by the number of values, then this, in some weird sense, looks like that. The integral is sort of like a sum of a bunch of values, and then this b minus a is the length of the interval, so the length that we're summing across. So in some sense, it may remind you of a usual formula for average, where you have a sum of a bunch of things divided by the number. And so that sort of intuition is what the book uses to justify where this formula is coming from. They start with Riemann sums and write things out. But I'll let you take a look at that if you're interested. I'd just like to go through an example of how we can use this. So let's suppose that we want to find the average value of cosine of x on the interval 0 up to pi. So, actually, let me do pi over 2. Okay, so by our formula, the average value of this function is going to be equal to the integral from 0 to pi over 2 of cosine of x dx divided by pi over 2 minus 0. This is going to be equal to, if we find the antiderivative of cosine of x, that is sine of x. So we'll have sine of x from 0 up to pi over 2. Then we'll divide by pi over 2. Sine of pi over 2 is 1, sine of 0 is 0, so this just becomes 1 over pi over 2, which is 2 over pi. So if we take a look at this function here, cosine, between 0 and pi over 2, and I want to know what is the average value, we see that it's 2 divided by pi, which is actually a little bit bigger than 1/2. So actually the average value of the function lies somewhere up here. So you might think because it goes up to a height of 1 that the average value of the function should be like 1/2, but it's actually not, because of the way the cosine function is shaped. There are more values that are closer to 1 than there are that are close to 0, so it ends up being a higher average. Okay, so that's how you can use definite integrals to calculate the average value of a function. And I think that's everything that I wanted to cover in this video.